Hello everyone. So, we will continue with textile reinforced composite. Now, we will discuss the textile structures which are used for advanced composite materials. These textile structures are basically known as prepreg or preform. Preform are basically the basic textile structure without the incorporation of matrix material. Only the textile reinforcing materials are there. On the other hand, prepreg is there, it is a preform, but impregnated or incorporated matrix materials are there itself. So, basic requirement of textile structures for advanced composite materials are, it requires high degree of structural integrity. This is required to prevent delamination, to increase resistance to interlaminar shear, distribution of dynamic stress, and obviously to facilitate ease of handling. Basically the preform, if we cannot handle easily, then it will be problem. Okay. So, here to have higher characteristics, better characteristics, so controlled distribution of yarns in the prepreg or preform is important. Proper orientation of yarns are required to have better characteristics. Normally in weaving the yarns are in crimped form, but for composite it is preferable to have crimpless yarn, which will actually enhance the tensile characteristics, better load share of the reinforcing component. Fiber volume fraction is another important requirement. So, higher fiber volume fraction is required for higher strength and flexural characteristics, and composite with well defined shape and dimensions is important, so that machining is minimized, wastage is reduced, and it is produced in lower labor requirement and less time is required. Suppose if we need one structure of circular cross section, circular shape composite, it is better to have a preform in circular shape, otherwise it will be wastage of material and proper shape. To get the proper shape we need machining. So, well defined shape and dimensions of the textile structure is required. Another problem of textile reinforced composite is that high modulus materials we are using, the property translation efficiency is much lower. That is the important consideration, because if we use a very strong material, but if the property translation is very low, then we have a problem. Okay. Also, in most of the textile conversion involves abrasion, tensile, compression, bending stresses. So, these stresses effectively damage the textile material, this reinforcing materials. Shear and torsional stress is exerted during braiding, which damage the yarns or fiber. Impact stresses in sewing and weaving also damages. Fibers like Kevlar and carbon, they lose their property significantly during compression or bending. So, the major contribution of textile structure is that hybrid yarn, if we can produce for thermoplastic composite, that will enhance the characteristics. I will discuss in detail. The hybrid yarn means the reinforcing material, reinforcing fiber is mixed with the matrix material in the form of fiber, and the hybrid yarn is produced with both the components. And textile preforms is another area where the major developments have taken place. So, we can directly convert the textile material in the shape of final product, so that we do not need any stitching, any joining, and which will ultimately result better quality of composites. The textile structures for fiber reinforced composites, initially fiber reinforced composite materials were principally fabricated using thermosetting matrices. The main disadvantages of thermosetting resins are the structural stability it is achieved by chemical reaction during curing, which is cross linking of polymer. So, that makes the matrix or composite it is brittle, and the transmission is basically permanent, as I have already mentioned. Lengthy curing cycle, low strain to failure, and limited shelf life at room temperature. These are the disadvantages of thermosetting resin. That is why the textile structure are developed nowadays using thermoplastic matrices. So, thermoplastic matrices, these are associated with physical intermolecular force, so that they can be reshaped again. On heating they can be melted, they have higher strain to failure as compared to thermosetting matrix, better fracture resistance, fatigue resistance is better, unlimited shelf life. See, in thermoset matrix we have discussed the limited shelf life. If we can preserve the thermoplastic matrix properly, the shelf life is very high, and this important characteristics, shorter and simple processing cycle involving only physical changes, no chemical. By heating it gets melted, and on cooling it is again solidifies, no chemical reactions are there. So, that makes the thermoplastic matrix so popular. So, all these positive features are there, which is these are the characteristics which make the thermoplastic matrix popular for modern composite manufacturing. But there are some difficulties. The main drawbacks are they are difficult to process because they have high melting viscosity. This high melt viscosity, due to this, the penetration within the structure is very difficult. Unlike thermoset matrix, initially their melt viscosity is very low. So, they can penetrate between the fiber space. The thermoplastics are difficult to incorporate into fiber and intersection point of yarn in fabric because of their high melt viscosity. if we want to reduce the melt viscosity, we have to increase the temperature, and that will in turn deteriorate the properties of the matrix. Also, if we want to incorporate in between the ion intersection point, we have to have very high pressure. So, heating the resin to a high temperature to achieve low viscosity can cause polymer degradation. There are few solvents which can be used for thermoplastic, but they are very expensive and are not generally environment friendly, that is why they are not so popular. So, what is the solution? So, to solve all this problem, the problem is that high melt viscosity, and we cannot reduce the viscosity by increasing temperature due to degradation problem. So, the main way, the basic system to solve these problems are to incorporate matrix within the preformed structure. The matrix polymer needs to be mixed with the high performance fiber even before preforming operation. So, that if we can do, then we can solve all these problems. Saturation of reinforcement with matrix prior to fabrication, which leads to the formation of prepreg. So, there are different ways to form prepreg by hot melt process, by slurry deposition, which is known as wet powder coating, solvent coating, commingling, powder coating. Of all these methods, powder coating and commingling have the potential for producing tow preg with considerable flexibility. So, other methods are also used, but if we want to convert this tow preg to the prepreg, which we need to have lower flexibility, and the lower flexibility is required for textile processing. So, if we have stiff tow preg, so we cannot form the fabric, or you cannot process in any other textile processing. So, in hot melt processing, the impregnation may be accomplished by forcing the fiber and resin through a die at high temperature under conditions that create high shear rate. Due to the high temperature of the process, the thermoplastic material can degrade. That is the problem of hot melt process. And solvent coating is that the matrix material is dissolved in a solvent, and then the tow is passed through that, and the tow preg is formed. The main problem is that the thermoplastics usually exhibit limited solubility at high concentration, and most engineering thermoplastic cannot be dissolved in low boiling point boiling solvent at room temperature. So, these are the problems. Slurry coating is also there, where the matrix, that is known as also wet powder coating, the non-solvent coating techniques, here the solvents are not used, the powder of the thermoplastic material are actually formed suspension in the liquid, powder suspension, which is in slurry form, and the toes are drawn through that slurry, and the thermoplastic materials are deposited on the surface. But all these three processes which we discussed, that hot melt, solvent coating and slurry coating, they are not that popular due to the reason that they sometimes they may degrade the polymer, or it is basically it is not environment friendly. But thermoplastic hybridians, they actually overcome all these problems. Here in the hybridian, there are different methods of manufacturing hybridians. These are the suppose reinforcing fiber, and mixed with fibers for matrix. This is matrix fibers, and reinforcement fibers. So, this hybridians actually it is a blend of both reinforcing fiber component and the matrix component, and they are flexible, and when heat is applied, the thermoplastic components melt and which impregnate the reinforcing component, and these are partially melted, if it is partially melted, and which forms amorphous reinforcing binder. In this case, the flexibility is still maintained, which helps in formation of textile preform, textile structure. So, after subsequent cooling, the system is transferred into rigid composite material. So, that if we can preform the in the form of woven fabric, if we use the hybridian and make woven fabric, then melted directly we can get composite material. Here main advantage is that we will get homogeneous distribution of matrix and reinforcing material, as matrix material is already present in the in between the reinforcing fiber. So, mass transfer distance of matrix is reduced drastically, which leads to faster and complete impregnation of reinforcement filament. There are various methods of manufacturing hybridian. This can be made using ring spun yarn, ring spinning process, rotor spinning process, air jet spinning process, commingling. So, there are various processes. In ring spinning, we can produce the hybridian using core spun technology, where these are the drafting rollers, okay, and here you have roving, of staple fiber, which is actually matrix fiber, and the reinforcement fiber, that may be filament or maybe staple reinforcing yarn, directly fed to the front drafting roller. Okay. From there, this forms coarse spun yarn. This is coarse spun yarn is formed here, where the reinforcing filament or yarn, which is not drafted, directly is being wrapped by the matrix fiber, which is thermoplastic fiber, and the coarse spun yarn is formed. So, separate creel for filament and roving is required, filament for reinforcement and roving is staple fiber roving for the matrix. Filament from creel is fed into the nip of the front drafting roller. The drafting roller receives continuous filament as well as the drafted strand of roving, the front drafting roller, okay, and then twisting. So, which forms the coarse sheath yarn. The main problem of this type of hybrid yarn is that it is a Barber pole effect is there, that is improper core coverage. In some places we will find that the core filament is not properly covered. That means, the proper matrix will not be formed, there may be a chance of void content in this type of matrix. Coarse spun yarn or cover spun yarn can also be produced using modified rotor spinning technology, where the filaments can be covered by the staple yarn. So, here again the problem of misalignment of the fibers, that is why it is not preferred for composite application. Drape spinning is the technology which is very widely used for technical textile application, and coarse spun hybrid yarns are used for thermoplastic composites. In this system, in the core again the filaments are inserted for reinforcement. The main advantage here is that the filaments are not being twisted. So, strength is retained and thermoplastic components are wrapped around the core component. In wrap spinning also, where the reinforcing fibers, reinforcing filaments are being wrapped by the matrix filament. So, suppose we want to produce the carbon filament with the polypropylene. So, carbon continuous filament will be mounted on a hollow spindle, and it will be allowed to pass through the hollow spindle, and around that say polypropylene thermoplastic filament will be wrapped, and this wrapping, in addition to the formation of core that sheath of thermoplastic, it provides the protection. So, during the further process, the carbon filament is protected by the wrapped polypropylene filament in the weaving or braiding. So, that they do not come directly in contact with the machine component, and also the core component remains twistless. Commingling is another process of thermoplastic composite hybrid yarn. So, here rapidly moving in the air jet is used to entangle the reinforcement filament and the matrix filament. Mingling process of two or more yarns to form a single strand of yarn can be defined as commingling. So, we can have more than two components if we want, and this mingling is generally done by air jet. So, commingling yarn consists of blended combination of reinforcing filament yarn and filament yarn spun from thermoplastic composite. The multi-filament yarns are scattered amongst one another at filament level. So, this is the commingling process where reinforcing filament, and this is the matrix filament, and this is the air jet nozzle where these are mingled together, and in commingling this filaments has to be multi filament, so that proper mingling take place. After that we can wind, and this commingled yarn we can use for converting to fabric or other structure. This commingling provides good blend of reinforcing fibers and matrix. The blend is then converted into fabric by any of the fabric production techniques like weaving, knitting or even braiding, and then this formed fabric is subjected to consolidation by direct compression molding. So, here we can control the fiber volume fraction also. So, main advantage of comminglings, the advantages are these toe pegs which we produce, these are very flexible and which is required for textile conversion. For weaving, knitting we need flexibility. As this matrix materials are present within the reinforcing fibers, so melt flow lengths are short. So, this result very much lower impregnation time, immediately it gets impregnated, that means the reinforcing fibers get impregnated. As we do not need to have very low viscosity, so less heat is required, okay. Only melting is enough, and as the flow length is less, so pressure requirement for composite formation is also less. So, lower void content is there due to already present matrix component within the structure. So, it is apparently it is a very good alternative for better quality thermoplastic composite. So, apart from these advantages there are few disadvantages. Main disadvantages are the toe pegs tend to demingled. So, because these are mingled due to the air vortex, so these are not that uniform. On stretching they may get demingled in some places. So, reorientation of matrix and fiber components, the reinforcing components are there, which actually results uneven distribution of resin that is resin rich and resin starved areas. So, this leads uneven characteristics and deteriorates the mechanical properties. Hybrid yarns are also produced from the air jet texturing techniques, almost similar process of air jet spinning, air jet texturing. So, where reinforcing fiber and matrix forming filaments are combined, similar to commingling process. Chemophil technology is also available, where it is a circular knitting machine operating with loopers that arrange around the guide bar and gives a tubular knitted structure which can cover any type of core yarn. So, here the knitted structure is covering the core yarn, and in the core yarn we can have both the reinforcing fiber and matrix filament also, but in the sheath it is a matrix filaments are there. Hybrid yarns are also made from parallel winding. It is the simplest process. Two components of hybrid yarns, that is reinforcing filament and matrix forming filaments, are laid side by side and wound in parallel form. But here the problem is that the penetration in between the multifilaments of the reinforcing fiber, so it is difficult. There is another technique, it is a Chappe technique, discontinuous reinforcing and matrix filaments surrounded by continuous matrix filament. So, that is also one technique of, typically it is a type of wrap spun yarn, little bit that type. Hybrid yarns are also formed by braiding. So, micro braided yarns, that is a very fine braided yarns are produced, consisting of tubular braided fabric. So, here the reinforcing filaments are normally kept in the core, covered by the thermoplastic filament. The next technique is that hybrid yarns from powder coating. This is the technique which has great potential in thermoplastic composite manufacturing for very high end application. The advantages are the produced toe pegs with considerable flexibility, which is critical requirement of textile processing. So, toe pegs basically here are the reinforcement component, the reinforcing filament covered by the powders of the matrix component. So, flexibility is always maintained. Now, let us see in hybrid yarn what we have seen. Suppose this is, these are the reinforcing component and these are matrix component. So, we assume that in hybrid yarn matrix component will melt and it will be in between this space of the reinforcing fibers, but we cannot guarantee here that all the 5 filaments will be coated or covered with the matrix component evenly, and also there are chances that the reinforcing component, this all initially although these were twistless or there is no crimp, it was straight, but after commingling process there will be misalignment or hybridian formation. So, definitely there will be chances of non-uniform distribution of matrix within the structure, but the powder coating theoretically there should be proper uniform distribution of matrix components. Suppose these are the multifilaments and there is no crimp, straight filaments, and the matrix powders are coated around the filament, each and individual filaments, and once it is coated and if we apply little bit heat, if we melt, this individual filaments will be totally coated with the matrix material. Here we are not talking about the total yarn, we are talking about individual filaments. So, if it is done properly, so individual filaments are coated with the powders and that will help in developing the better quality of thermoplastic composite with much more uniformity. As the individual filaments are coated, so melt flow length are very short and this results very much lower impregnation time. It again requires less heat and pressure for formation of composite, and most important thing is that this results very low void content of the composite. Other hybridians, there are chances of void content, higher void content due to non-uniform distribution of matrix fiber, but here the void content, chances of void contents are least. Now, if we see the comparison between powder coating and commingling, the commingling yarn, as I have mentioned, it is although uniform at the time of production, but in further processing due to application of stress, demingling take place, which results resin rich and resin starved area, that is non-uniform distribution and which leads to poor mechanical characteristics due to higher void content. The other disadvantage of this yarn is that normal flow of resin as compared to axial flow in powder coating. In powder coating we do not need normal flow because all the individual filaments are coated, but in this commingling we have actually normal flow of resin. Now, I will discuss the powder coating technique. The powder coating is done through fluidized bed. What is fluidized bed? In this process the air passes from a plenum chamber through porous plate in a container containing finely ground thermoplastic powder. As the volume of air increases, the bed fluidize and powder particle become suspended, forming clouds of powder. Now, let us see here, these are the powders of thermoplastic matrix. Now, air is being supplied at the bottom. Now, gradually we will see this bed will become fluidized and the powder will start escaping from that. This is just like it is boiling. So, this and due to the air supplied and while doing, the particles will form cloud. So, as the volume of air increases, the bed fluidizes and powder particles become suspended, it will start forming the cloud of powder. So, at this stage the powder behaves like a fluid, it will just like a fluid, just like it was just like boiling, and it will, the particles will have mobility, and the heated preform after coating, when it passes through the oven and this powder melts and covers the surface of the reinforcing fiber, and after that it is cooled down and the prepreg it is a so flexible we can wind in a package. So, this is the powder coating method, basic method, and I will continue discussing the powder coating techniques and detail the methods of powder coating in next class. Till then, thank you.